Good morning, everyone. My name is Weina. I'm now assistant professor from Stevens Institute of Technology. So today I'm here to talk about the AI-assisted design of low-carbon, cost-effective, ultra-high-performance concrete, or UHPC in short. So this work is done together with my colleague, Dr. Bao. For now, there's two methods to design the UHPC. The first is to maximize the particle packing densities of the UHPC based on, do I have a pointer? No. So, thank you. So based on a model, something like this. But these methods could not guarantee the high performance to all the properties, such as the tensile properties or the shrinkage. And because of that, a lot of people also use the performance-based methods. So this method is to achieve the optimal performance based on step-by-step testing. So as you can see, this method is time-consuming. It involved a lot of experiment. So it is labor-intensive. So it is important to develop a more efficient and effective methods to design the UHPC. Therefore, we developed the AI-assisted design framework for auto-discovery of low-carbon, cost-effective UHPC. So the first step of this framework is that we have to obtain large enough and good enough data for high accuracy of the machine learning model, and then we will develop the machine learning model for prediction. So for this case, the input is the concrete design variables, output is the concrete properties. And based on the good established machine learning model, we will embed the optimization algorithms so that we can input the target properties and output the optimal design. So the prediction of UHPC properties is actually a very typical regression task. But for us, we need to consider many design variables. So we require high-fidelity machine learning models for this high-dimensional problem, the high-dimensional regression task. So two sets of data are usually used for these models. First is the mixture design variables, include the types of ingredients, the mixture variables such as the water-to-cement ratio, the processing scheme such as the curing time, and the second set of data is the UHPC properties, include the fresh properties and the hardened properties, such as the mini-slump flow, flow time, flexural strength, durability, and shrinkage, and so forth. So to facilitate the AI-assisted design, we have to answer several critical questions. The first question is, how can we efficiently obtain the large enough and good enough data for high accuracy of the machine learning model? The second question is, we know that for now we have a lot of different types of machine learning models developed. And how can we select or develop the most appropriate machine learning models? And the third question is, how can we optimize the UHPC mixture design by considering many design variables, not just the compressive strengths? And the fourth question originates from the fact that for now more and more solid wastes are involved into the concrete design for sustainability. So how can we deal with the large variations in the physical and chemical properties of the solid wastes? So to address those questions, we developed AI Designer, which involved the AI data collector, AI data generator, AI data processor, as well as the AI auto learner, optimizer, and data presenter. So the AI data collector was developed to automatically collect the available data from the published documents, such as the journal papers, the conference proceedings, and the reports, and etc. And the collected data can be automatically updated through tracing and extracting data from the new publications. So the benefit of the data collector is that it can automate the data collection process in high efficiency and high accuracy. And before we have that, we had our students to collect 1,000 data manually. So it took them 1 month to do that. But with this method, we just need 1 hour to collect 1,000 data. So it saves us a lot of time. And then another benefit of it is self-updatability. It has self-updatability, which can improve the accuracy of the machine learning data, machine learning model by considering increasing database. And also, it enables the consideration of the new materials, such as new types of solid wastes. So this is important. As you can see, over the years, the dimensions of the input variables, especially the variables in the types of materials, significantly increased. And another benefit of it is it enlarged the design space for lower carbon footprint and lower cost, because more solid wastes are considered. And from our studies, we found that the self-updatability significantly enhances the accuracy of the machine learning models over time, as more and more data is collected. And in the meanwhile, the life cycle cost and carbon footprint are reduced, again, because more new types of solid wastes are considered. So the AI data collector helps to reduce the time in collecting the data, but still, for new types of materials like the UHPC, the data is still very limited. But for the machine learning models, as you can see, the accuracy is highly dependent on the amount of data. So because of this, we proposed the 2 methods to generate new data. So the first method is to use the established theories or equations. Here shows an example. This is a very well-established relationships between fiber parameters and the strain. So we can input like different values of the fiber parameters, and we will get a series of the tensile strain. So that is one type of new data. And the second method, we use the advanced machine learning techniques, such as the GAMS model, to transform the existing real data into the artificial data. So the idea is similar to transform an image to the style of Van Gogh's Starry Night paint. So we use new image to generate some artificial image. So the generative model can learn from the existing data so that it can generate the artificial but realistic data. And then we combine the AI data with the real data to a synthetic data. So this enriched synthetic data will be used to train our machine learning models. So now we know how to obtain large enough data. So the next question is, how can we ensure the high quality of the data for higher accuracy of the machine learning model? So we know that anomalous data is usually generated due to some errors during our experimenting or entering data or processing the data. But the good thing is that the data science, based on the data science, the anomalous data have different features from the normal data. So we can rank the data and differentiate the anomalous data from the normal data through the supervised or unsupervised learning. However, occasionally, the normal data will be treated as anomalous data because we identify those data based on data science, not material science. For example, if we use the data-driven methods to identify human beings from many objects. So it may identify a people without hair as anomalous data because the majority of the data have hairs. So, but that's not true. So even people without hair, it's a normal data. So to properly remove the anomalous data, in order to improve the accuracy of the machine learning model, we defined a contamination ratio, CR, which is defined as the percentage of anomalous data in the data set. So from the parametric studies, we see that there's an optimal contamination ratio that will lead to the highest accuracy or the minimum errors. So it is not the case that we remove all the anomalous data, we get the highest accuracy. So we found that when we have the contamination ratio of 7.6%, we get the highest accuracy. So the next important issue for the machine learning model is the variable selections. So if we included dependent or redundant variables into the machine learning model, so we will make the model very complicated and not accurate. But if we don't consider the necessary variables, we also will not make the machine learning model very accurate. So there's two criteria for the selection of the variables. First, the design variables should be independent of each other. We cannot consider water content and the water to cement ratio at the same time. And second, the design variables should be highly correlated to the concerned concrete properties. So from one of our studies, we investigated a number of input variables on the prediction accuracy of flexural strength of UHPC, and we consider 21% variables has higher accuracy when we consider 24. So in terms of model selection, for now, as I said, there's many different types of machine learning models. So categorized by the individual models and ensemble models. Overall, ensemble models have higher accuracy or better performance than the individual models, but it should be important to note that the ranking of the models should be dependent on the cases, the special cases. So the accuracy of the machine learning models is highly dependent on the specific case, the specific problems, the adopted data, or the feature of the data. So in our studies, we automate the development of the high-fidelity machine learning models. So for this task, it involved the automation of model selection and combination, the hyperparameter optimization, and the model complexity minimization. So compared to the current practice that input the raw data, normalize the raw data, and train the specific machine learning models, our methods automates the data processing, machine learning selection, model selection and control, training and validation, and automatically output the high fidelity model. So as you can see here, compared to the other methods that we listed here, our methods show a higher accuracy in accordance with the Taylor diagram. So once we have the high fidelity machine learning prediction models, we can move on to the optimization. So to design low carbon and cost-effective UHPC, it is a multi-objective optimization problem. So we should simultaneously optimize the environmental, economical, and mechanical properties. So to do that, we should obtain large enough concrete design variables and forward the data to the machine learning models. And after training, it will give a very high accuracy prediction on the concrete properties. And also, we investigated inventory data and use that to calculate the carbon footprint and cost and embodied energy of the raw ingredients. And after that, we will define our design objectives, sometimes also define the constraints. And then we will apply the optimization algorithms and then output the optimal design. So the evolutionary optimization algorithms is used to search for the optimal solution through minimizing the objective function defined based on the design objective. So here shows the example. So we have considered many types of solid wastes or different types of materials. And the design constraints is the mini-slump flow should no less than 260 millimeter. And the 28-day strength should no less than 120 megapascal. And we have set the design objectives as minimize the unit cost, the carbon footprint, and maximize the compressive strength. So our result optimum mixture shows that we reduce the cost by 65% and the carbon footprint by 56%. So however, the applicability of the machine learning model is still very limited, especially when we consider some solid wastes. So the reason is that the physical and chemical properties is not considered into the machine learning models, but the physical and chemical properties for even the solid wastes, the same name, like a fly ash, are very, very different. The physical, the particle size distribution or the chemical composition, very different. But that are not considered in the machine learning models. Therefore, we create an artificial language to describe the physical and chemical properties of these wastes. So these properties will be transformed into numerical data set so that the computer can understand for the machine learning and so on and so forth through the artificial language and the text mining. So for the artificial language, we first define some symbols to describe the chemical and physical properties, and then we assemble the symbols into sentence and then the essay. So we will input the essay and output the corresponding concrete properties. So we use machine learning, deep learning for the concrete properties. And one of the important capability of these techniques is that it can also investigate the chemical reactions. So as you can see here, the heat maps. So we can evaluate the interactions between different chemical compositions, like different oxides. So the higher interactions, meaning the higher chemical reactions or stronger chemical reactions. So that will help us to unlock some new chemical reactions. So here shows the conclusions. So if you want to know more details of the things I just presented, here is our current publications. So here is the main contributors, Dr. Yi Bao, Dr. Surush Mahjoubi. So he was a PhD student of Dr. Bao. He's now a postdoc at MIT. And Dr. Pengwei Guo is one of my PhD students. And also thanks to our external sponsors. Sorry, I'm a little long, but thank you very much. That's all. Thank
you. I think we have time for one question.
Hello, my name is Yong Hao. I'm from Sandia National Labs. Thank you for a really good presentation. This was very interesting.
Thank you.
And I have two questions. First question is, what metrics have you considered for the automated data selection process?
What metrics?
Yeah. What did you consider for?
Metrics?
Uh-huh.
Metrics for the optimization?
What parameters have you considered, when you model for the automated data selection?
So we considered the variables, the materials types, the mixture variables, content, cement content, the different materials content, and also some curing schemes.
No, I meant when you distinguish, between the normal and anomalous data, what did you consider?
Normal? I couldn't.
Your anomaly detection?
Uh-huh. Anomalous detection?
Yeah.
Okay.
I think you had your contamination ratio.
Uh-huh.
Is this your only?
So the contamination ratio, how differentiate the normal data?
Right.
And okay, sorry, I didn't get your question. So, so here, as you can see here, so we use the supervised and unsupervised modeling to detect the anomalous data. This is based on the data-driven methods.
Okay.
So it will have different features. It will can identify by those models. So you can differentiate the normal data. The anomalous data from the normal data.
I think I meant, how did you consider those threshold, between the normal and anomalous data set? But I think
maybe we can discuss later.
Yes,
I
right.
think there involved more complication
Yeah,
there.
sure. And then the second question is, can you share what you learned from machine learning model selection phase of your studies?
So the machine learning model selection.
Yeah.
Okay. Elaborate it.
What have you found?
What have I found?
Yeah.
So instead of choose a specific machine learning models, we develop the methods to maybe select, depending on the data, the feature of the data, we will select the most appropriate or combine several different models together to get a better, more accurate kind of models.
So I think more specifically, for your study, for example here, what did you find? Which model you find more appropriate for your
For more
analysis?
appropriate?
Uh-huh.
So for us, we actually, this is one case. So we combined several ensembled models, and that shows a higher accuracy. But what is the models that we combined? I forgot, so I should show you our papers. But combination of several ensemble models shows a higher accuracy in
Oh, you
our
tried to
case.
combine. Okay, thank you so much.
Hope I answered your question. Thank you.